Då ska vi se, då är klockan 14.00 men vi har fler som är anmälda så vi kanske väntar några sekunder till innan jag kör igång. Bless you.
Thank you.
Då ska vi se, då tänker jag att vi börjar dra igång. Vi har betydligt fler anmälda till det här webbinariet men det är inte alla som har dykt upp än. Men vi kör för klockan är nu 1 minut över. Jag heter Ingrid Nordgren och jag är föreståndare för Svensk kunskapscenter för förnybara drivmedel som tillsammans med Energimyndigheten driver samverkansprogrammet Förnybara drivmedel och system där vi nu idag kommer att presentera resultat från ett projekt. Och vi spelar in det här webbinariet så var medvetna om det. Om ni ställer någon fråga eller så vet ni att det spelas in. Och lite bra att veta då. Håll mikrofonen avstängd om du inte pratar. Om ni har trög uppkoppling, stäng av videon. Och om ni vill ställa en fråga så ställ den i chattfunktionen eller använd räck upp handen-funktionen. Frågorna samlas däremot till frågestunden efteråt. Och har ni något annat tekniskt problem så kan ni vända er till Emmy, våran kanslikoordinator, och hon lägger också ut kontaktuppgifterna i chatten här. Och den här presentationen som kommer att visas om projektet senare här, det kommer att läggas ut på våran webbplats och även den här inspelningen kommer att läggas ut på våran YouTube-kanal. Så programmet idag, jag kommer att hålla en inledning på 10 minuter och sen så kommer vi få höra Efthymios berätta om projektet ungefär en halvtimme och sen så har vi en frågestund efter det då. Så lite grann kort om samverkansprogrammet Förnybara drivmedel och system. Vi är inne på vårt sista år på den här 4-åriga programperioden. Och det innebär att vi kommer att ha många projekt som avslutas här i år och vid årsskiftet. Så anmäl er gärna till vårt nyhetsbrev så får ni följa när det kommer projektresultat. Det har då som sagt varit en 4-årig programperiod och vi har haft en total budget på drygt 44 miljoner. Där Energimyndigheten har finansierat 22 miljoner och F3s parter 11 miljoner. Och sen så har vi ytterligare då samfinansiering från olika parter. Och alla medel är tilldelade, alla projekt pågår eller är till och med avslutade, men det har totalt varit 26 projekt i den här etappen. Och syftet med programmet är ju att vi vill göra analyser som kan stödja vetenskapligt underbyggda beslut när det gäller omställningen av transportsektorn och då specifikt förnybara drivmedel och hur förnybara drivmedel kan bidra till den omställningen. Och det andra syftet är ju då att öka systemförståelsen hos politiker, myndigheter, industri och andra organisationer. Vi har sett att samverkan är väldigt viktigt. Så det här programmet bygger väldigt mycket på samverkan, inte bara mellan Energimyndigheten och F3 utan även samverkan i de specifika forskningsprojekten mellan olika forskningsutförare och industri och institut och näringsliv och andra relevanta aktörer. Och det kan vi se även i det här projektet då, där vi har flera olika aktörer som bidrar. Samverkansprogrammet har pågått i 2 etapper. Det här är den andra etappen. Så totalt sett så är det då 8 år som det har hållit på. Och inom ramen av programmet så har 55 forskningsprojekt genomförts eller pågår. Och vi har haft 7 öppna konferenser och planerar för en 8:e konferens någon gång senare i år eller möjligen i början på nästa år. Och det är många olika organisationer som har deltagit. 80 olika organisationer har deltagit i de här projekten. Och hittills så har det lett till minst 38 vetenskapliga publikationer. Lite kort om F3 då, ni som inte känner till oss sedan tidigare, så inom F3 så samverkar industri, högskolor, institut och myndigheter för en långsiktigt hållbar drivmedelsförsörjning till transportsektorn. Och vi har 16 olika parter idag, och på industrisidan så är det Prim, Neste, ST1, Lantmännen och E.ON som är drivmedelsproducenter. Och sen har vi Scania och Volvo som tillverkar fordon. Och på högskole- och forskningsinstitutssidan så har vi de organisationer som är framstående forskningsmässigt inom de här frågeställningarna. Och det är ju då Lund, Chalmers och KTH, det är SLU och sen Bio4Energy. Och Bio4Energy är ett samarbete mellan Umeå universitet, Luleå tekniska universitet och SLU i Umeå. Och instituten som vi har med är IVL, RISE och VTI. Centrumvärd för det här, det är Chalmers industriteknik. Och vi samarbetar då med Energimyndigheten inom ramen för samverkansprogrammet. Och vi har också finansiering från region Västra Götaland när det kommer till kunskapsspridning och samverkan. För vi har 3 viktiga uppgifter som vi ser det. Kunskapsbyggande med att ta fram forskningsresultat är basen i verksamheten, och det är där då som vi bedriver samverkansprogrammet med Energimyndigheten. Sen så har vi väldigt stor vikt också på att sprida kunskapen som kommer ut ifrån de här forskningsprojekten, och så samverkan mellan olika aktörer inom F3 och även utanför F3. Så som sagt, anmäl dig gärna till vårt nyhetsbrev. Det kan ni göra på vår webbplats f3centre.se. Och då var jag färdig med min korta introduktion, och det är dags för presentation av spännande forskningsresultat. Det här projektet har vi kallat för Bioflex. Det handlar om biobaserad flexibel produktion av drivmedel i en kombinerad pyrolys- och förgasningsanläggning. Och det är Efthymios Kantarelis på KTH som har varit projektledare. Det är han som håller presentationen här. Men från KTH har dessutom Claes Engvall deltagit, och sen så har vi Andrea Toffolo från LTU och Rolf Ljunggren på Cortus Energy. Så det här ser ni ett exempel på att vi har aktörer från flera olika organisationer som deltar. Och rapporten finns att ladda ner på vår hemsida. Och där finns dels en fullständig slutrapport, men också en så kallad executive summary som sammanfattar forskningsresultaten. Då ska jag byta presentation så att vi får, då ska vi se. Då tänker jag now I'll switch to English because the presentation we will hear now will be in English, and please, Efthymios, you could take control and start switching slides when you when you want to. So go ahead.
Okay, thank you very much. Good afternoon, everyone. I'm Efthymios Kantarelis, and I had the privilege to manage a project within the frames of F3 program, which, as mentioned, was carried out with Luleå Technical University and Cortus Energy and KTH. The project is named as Bioflex, bio-based flexible production of transportation fuels in a combined pyrolysis gasification plant. The topic is quite technical, however, I will try to make it as simple as possible. Therefore, in the beginning, I will try to give a brief introduction and background in order to show the rationale about this project. So, as we know, by 2045, Sweden has set zero net emission goals, and thereafter we should try to achieve negative emissions. In parallel, the emissions from domestic transport should be reduced by 70% in comparison to the emissions we had in 2010. But what is really important with the domestic transport emissions? Well, they represent 30% of the total greenhouse gas emissions in Sweden today. And out of which 98% is coming from road transport, actually. Therefore, we can understand that it's really important to take care of the emissions in the transportation sector if we want to achieve the 2030 and the 2045 goals. Here, the biofuels, of course, play a very important role for this transformation, but the question we have here is whether we are really able to achieve these goals. The numbers needed to achieve these goals are somehow high. We need around 3 million cubic meters of drop-in biofuels by 2030. And by drop-in biofuels, we mean the fuels that they have the chemical structure and composition with the ones that they come from fossil-based resources. And we see that this number currently cannot be met with the existing production routes. In the same wavelength, actually, a recent report by International Energy Agency indicate that in order to provide the much larger drop-in biofuel volumes that we need to commercialize thermochemical technologies that utilize biomass feedstocks. So in order to achieve this 3 million goal, we need to use forest residues and forest resources. But thus Sweden has the potential to achieve this number of fuels via thermochemical processing. Well, the answer is yes. The forest sector has a very high energy potential in Sweden, and logging residues and sawmill byproducts account for around 7 to 27 terawatt hours in energy potential, which almost covers the 3 million cubic meter demand for biofuels in Sweden. Therefore, the forestry sector and the utilization of the lignocellulosic residues is crucial for reshaping the transport sector. The production will be accelerated and enhanced by the commercialization of thermochemical treatment. But what do we actually mean by the thermochemical treatment of biomass for production of drop-in biofuels? If we consider the biomass resources, the forest residues, we have two main thermochemical routes that they can achieve production of drop-in biofuels. And these include the gasification, where we have the biomass subjected into high temperatures environment in the presence of air or oxygen, and gives rise to gaseous molecules, also called syngas. And those molecules that they are formed, they undergo some synthesis process. Typically, the synthesis we use is the so-called Fischer-Tropsch process, which is a process invented almost 100 years ago by two German chemists, Franz Fischer and Hans Tropsch. And the product of this synthetic process is a fuel which is identical to the fuels we can get actually from oil. The other thermochemical route that we typically use for biomass processing is the biomass pyrolysis, which is practically the thermal decomposition of biomass. We heat the biomass in the absence of any oxidizer, and the products are actually vapors or liquids if we cool them down. And they undergo another type of treatment and upgrading or synthesis process, if you like, that produces a drop in biofuel. So since the roots are there, what is really the problem with them? Why don't we go into big scale and produce the volumes that are needed? The problem lies in the utilization of carbon that those processes have. The gasification route, in particular, allows around utilization of around 30% of the carbon that is actually contained in the biomass. While the biomass pyrolysis route, depending on the upgrading or the conversion routes that we use to produce the drop-in biofuels, allow us to convert from 17 to 35% of the biomass contained carbon. So as we see, almost 1/3 of the carbon that is actually present in the biomass can be converted into liquid fuel. So if we are to achieve the goals for 2030 and replacement of fossil-based transportation fuels, we need to be more efficient in the conversion of the biomass contained carbon, given that the availability of biomass is sometimes limited. So the BioFlex project actually tried to answer 3 questions. Those 3 questions is whether we can really improve the carbon utilization in the biomass conversion, and if so, what do we really need to do in order to do that? Do we really need to reinvent the wheel or invest in research time for new processes that can give us better carbon utilization? We have to think that we need to act fast in order to achieve the goals that we have set for 2030. 2030 is not far. So it has to be processes that they can be implemented relatively fast. And the results should be, of course, tangible within a very short time. Of course, other processes can also be researched in parallel to these activities, but we need to act now. And the third question that we try to answer is, what happens with the fuel mix demand? How can the process that we design today, and they are targeting to 1 or more products, can meet the future fuel mix demand in Sweden in particular? Here we see the volumes of fossil-based gasoline and diesel that have been used in Sweden the past years, and a linear projection with 2030. We see that the fuel mix demand shifts towards the diesel production. We still, though, have a considerable demand for gasoline still in place even by 2030. So the process, the concept of the BioFlex project actually is to try to answer all of those 3 questions. That means to try to provide efficient carbon conversion with processes that they can be implemented fast in a short time, and thirdly, in processes that they can produce fuels or products that they can be flexible in composition in order to meet the market requirements. So the BioFlex concept includes the biomass treatment via pyrolysis mainly, and then with synergies with gasification, that is the solid carbon that is produced in the pyrolysis sector, giving a feedstock for the gasification, and gasification itself providing energy for the pyrolysis section. And ideally, those 2 primary products for those 2 processes, the pyrolysis vapors and the gasification gases, ideally would need 1 synthesis process in order to produce the drop-in biofuel. But if we now take a closer look at the synthesis process, is it really realistic to consider that we can have one synthesis process for those two primary streams of the thermochemical treatment of biomass to produce the drop-in biofuels? Unfortunately, the answer is no, because given the completely different chemical nature of those two streams, the gases from the gasification and the vapors from pyrolysis, is almost impossible to find one synthetic route to produce the drop-in biofuels. However, instead, we can produce some platform molecule or building block from both streams that can instead be effectively converted into a drop-in biofuel, and this process can also be flexible in terms of product composition. That molecule has been identified, and it's actually not a molecule but a group of molecules, the olefins, which are light hydrocarbons with carbon numbers ranging from 2 to 4. As an indication, gasoline has carbon numbers of 6 plus, and diesel carbon numbers of 11 plus. And these molecules can be converted efficiently into both gasoline and diesel range hydrocarbons or drop-in fuels via the mobile olefins to gasoline and distillate process. This process was developed by Mobil, now it's called ExxonMobil, in the late 70s after the diesel crisis. But why specifically olefins? What is particular with those types of molecules? Well, first of all, they can be converted into hydrocarbons with a very high carbon efficiency. Typically, more than 95% of the carbon contained in the olefins can be converted into liquid fuels via the Mobil process. And of course, they are a chemical commodity of high demand, which actually can give rise to the production of different chemicals, polymers, lubricants, and so on. And this actually gives an extra value to the concept of the bioflex, because even after a complete electrification of the transportation fleet, there will still be a market for the product, the olefins that this process will produce. Thirdly, in a similar wavelength again, we can produce also jet fuels of high quality via the Mobil process, which also is an advantage if we consider that the aviation fuels will probably be longer in the market as compared to the transportation fuels. So now it is clear why olefins was chosen, and in this project we investigated three main scenarios. The first process concept included the gasification route for biomass, the standalone gasification route, where the biomass is converted into syngas using oxygen as an oxidizer, and then the produced syngas is converted into light olefins, and then the olefins converted into transportation fuels via the Mobil process. The second process concept is a combined pyrolysis and gasification route, where the biomass is pyrolyzed and the solid carbon is converted into syngas via the gasification with oxygen. And both the primary products from the gasification and the pyrolysis are then converted into olefins, and then the olefins again are converted into drop-in biofuels. The third process that was investigated is very similar to the process concept 2, with the difference here that air is used instead of oxygen for the gasification part, which means that in the second process concept, the nitrogen is separated from the air before the gasification, while in the process concept 3, the nitrogen is separated downstream the gasification before the syngas to olefins conversion process. In all the process scenarios investigated, small to medium scale plants were considered, 5 to 50 megawatt biomass thermal input. Roughly 1 ton per hour of biomass, just to give you an idea, is around 5 megawatt of size. And for every concept, 2 product mixers were considered, those corresponding to the 2020 and 2030 fuel mix. When we say fuel mix, we refer to a ratio of gasoline and diesel. One important and technical thing that has to be actually pointed out is that during the conversion of the syngas that is generated from the gasification to olefins, adjustment of the composition of the gas is needed, because typically more hydrogen is needed for such conversion. And therefore we use part of the produced CO from the gasifier to produce hydrogen, and at the same time we produce CO2. And this is important to understand the results that we have obtained by analyzing those processes. So if we now go to the main process results, process analysis results, we see that the combined pyrolysis and gasification scheme, which is represented in process concept 2 and 3, gives considerably higher carbon efficiencies, almost 40%, while the standalone gasification of biomass gives a carbon efficiency of around 30%. Almost 30%, which is typical of a gasification process for production of drop-in biofuels. Similarly, the energy efficiency for process concepts 2 and 3, which are the combined pyrolysis and gasification processes, give almost 50% of energy efficiency, including also the electricity needs. So those numbers, from those numbers, it's clear that the combined pyrolysis and gasification plant actually gives a better performance and a better overall efficiency. One thing which is crucial though for such a process is the performance of the gas separation units, because any carbon losses in those units actually is very crucial if we want to achieve the high carbon efficiencies here. Here it has to be mentioned that in all the modeling and simulation approaches we had in this project, several other considerations were taken and best practices that they are used in industry, even though that sometimes the simulation results didn't indicate that different approaches were needed. We used the best industrial practice from similar processes. So in order to give a more realistic touch into our results and not merely based on what we get from our simulations. But what do these numbers actually mean in terms of the 2030 goals? What do we really achieve? If we translate those numbers into fuel production, actual fuel production, we see that we can achieve almost 300 liters or more than 300 liters of total liquid fuels if we combine the gasification and pyrolysis routes. And also we see that the direct CO2 savings by substitution of the fossil-based fuels is almost 800 kilos per ton of biomass that is utilized in the process. Just for comparison, 1 ton of CO2 roughly corresponds to almost driving 6,000 kilometers with a fossil-based diesel car. We see that the adjustment in process condition to match the 2030 and the 2020 fuel mix do not affect the efficiencies nor the CO2 savings in any of the process concepts 2 and 3, which is indicative of the flexibility, of course, of the mobile process. And that also means that the process can be adjusted into the situations and the market situations quite easily. And mainly, the main thing that it has to be done is to change recirculation rates in the final reactor without changing anything in terms of process layout or equipment. During the conversion of the CO2 or the adjustment of the composition of the gasification gas, the CO2 was captured using an advanced adsorption technique. For those who are interested, the CO2 enhanced absorption water gas shift reaction was used. And we see that for the process concept 1, which is the standalone gasification, almost 900 kilograms of CO2 per ton of biomass are saved. This is reasonable if one recalls that this particular process concept has the lowest degree of carbon utilization to the liquid fuel. Now we see why, because a lot of carbon is converted in this process step into CO2. For process concepts 2 and 3, the capture is smaller because, of course, the carbon is mostly is utilized for production of liquid fuels. A secondary look into the CO2 savings from the production of green olefins shows that almost 200 kilos of CO2 can be saved if olefins are produced from biomass compared to the naphtha cracking that is typically used today. That results indicates that most of the CO2 savings can actually come from the direct substitution of the transportation fuel if we want to achieve the 2030 goals. And replacement of olefins should be considered as a secondary target. So is this really everything so perfect with this process? Why don't we commercialize it then? Well, the answer comes from the process economics, unfortunately, because economic analysis showed that, especially for small-scale plants, the production cost is really high. It's for the standalone gasification is 26 almost crowns per liter of liquid product. But we see that by 2030, the prices are a bit lower because of the different fuel mix and the different hydrotreatment requirements. The production costs for process concepts 2 and 3 are lower, still high, but are lower when they are compared to the standalone gasification. But still, we see that even for the 50 megawatt size plant, the production costs are around 10 to 12 crowns per liter. And indicatively, for in January 2021, the average cost for fossil gasoline was 4.91 crowns per liter, and for diesel it was 6.87. So we see that if we just compare the production costs, this process is really off. So if we try to wrap up everything we have seen from this analysis, it was clear that the combination of pyrolysis and gasification can provide considerably higher efficiencies compared to standalone gasifications or even standalone pyrolysis routes. And this is due to the synergies that they exist between the thermochemical treatment of solid biomass, but also due to the synergies that they can exist during the conversion of the primary products that we get when we try to convert them into olefins, and that is the conversion of the pyrolysis vapors into olefins and the conversion of the gasification gas into olefins. The synthesis of olefins as an intermediate is promising because it offers a flexible production of biofuels that can meet the fluctuating fuel market. And the adjustment of the process conditions does not include any additional carbon losses or any other energy penalties. All of the processes were actually heat self-sufficient by combusting some off gases of the process here and there. However, the syngas to olefins part requires several reaction and separation steps if we are to achieve high efficiencies, which of course increases the complexity of the concept. The synergies between the drop-in biofuel production routes, the thermochemical-based drop-in biofuel production routes, and the renewable hydrogen production will boost the carbon efficiencies, the overall carbon efficiencies, because we can replace the step where we adjust the composition of the syngas. Actually, that conclusion was the trigger for doing extra study to investigate the effects of introducing an electrolyzer in the system. And I can tell you that the results were really remarkable, offering way higher efficiencies. The CO2 utilization is also important here because especially if the renewable hydrogen production is included, especially if we want to produce olefins for chemical productions, because then we can also consider that the product that we produce has a longer lifetime, so we can store the carbon more efficiently in the society. However, the production cost is too high when compared to fossil-based petrol and diesel. And therefore, we should balance the economic performance with environmental goals in order not to simply reject such a process because of economical reasons. Future cost reductions, especially in hydrogen generation from electrolysis, can offer at least a 3 to 5% reduction in the production cost of the final product. While the direct mitigation by biofuels, CO2 mitigation by biofuels production should be the main goal for achieving the 2030 goals, while policies should be will put in place in order to motivate CO2 net removal from green resources, which can be such as paying dividends to negative CO2 emitters, for example. That was all from me. I would like to thank all of the project partners, and of course F3 Energy Agency for the support, and especially Ingrid and Emmy for their help during the completion of the project. Thank you.
Okay, thank you very much, Efthymios. I have some short questions in the beginning here of the discussion when it comes to just a clarification when it comes to the production costs. The production costs that you present here are the production costs for the olefins, or is it for the actual? No. Is it for the final renewable diesel or renewable
the final
gasoline?
gasoline and diesel? Yes, it includes the final step. Yes.
Yeah. And then another comment from me then regarding the production costs. I think you're making yourself a little bit injustice when you compare it to fossil products, because I think if you compare it to other renewable fuels, then it's not such a bad or such a high production cost.
Yeah,
So,
well, yes, you are right about that, and I had such discussion. But the main goal here, if we want to actually achieve the goals for 2030, is to substitute fossil-based fuels, and the biofuels themselves can actually contribute to achieving this goal. So we didn't consider the other types of biofuels as competitors, so to speak, in this process. So we wanted to compare with the fossil-based resources.
Because I was thinking, if you look at the Swedish perspective, where we have the reduction quota system, there the suppliers are forced to add more and more biofuels, and then even a higher cost could be, I would say, competitive. Was my thought on that. But I see we have a question here. And let's see who it was. I have to show my participant list here. So Peter, go ahead if you have a question. Please turn on your camera and also, so if you want to.
Yep. Yes, thank you. It was a very nice presentation. This is Peter Skoglund here from the small company Earth Reduction. I was thinking about two things, maybe this production cost, so to say. Is it what is the bottleneck, so to say, in your production cost? Is it the raw material? How much do you pay for the raw material? What is the raw material really, and how much do you pay for it? Is that the main bottleneck, so to say, for the cost calculations?
Yes, I mean the price is mainly dependent on the biomass price, on the feedstock price, not so much on electricity, because I can say that the heat integration of the plant is very good, and more or less there is no need for extra electricity. So the main cost comes from, of course, the very high capital investment, and also from the feedstock cost.
And what is your feedstock, and what is your price for? How did you calculate? Did you calculate energy value on that one? How did you calculate that price?
The price was taken from the literature for it was an average typical European value, which was I don't remember now on top of my head. Yeah, sorry, I don't remember, but you can find it in the report. If you give me 1 minute, I can look it in the report and I can tell you the number if it is of interest for you.
And what was the biomass?
The biomass considered was a typical forest biomass, because we were considering of utilizing mainly sawdust from paper mills, for example. So it was a typical composition of sawdust, so to speak.
And what I mean, we are, for example, focusing on this circular bioeconomy, and I was thinking here, because you have this high production cost, you cannot use that strategy here somewhere, but you can utilize, you can manufacture also some more high value product in your process somewhere, so you get a better process economy.
Yeah, I mean, it was in mind also to consider selling the olefins without utilize them for transportation fuels, but that would reduce, as we saw, the CO2 savings. If we were considering of substituting, for instance, the naphtha they use for producing of olefins. So from that point of view, this calculation, yes, maybe it makes sense. Part at least of the olefins that they are produced to be sold as a commodity chemical, which actually has a quite high value, and that would of course improve the economics.
Yeah, and there was no other product you could produce with, say, even more high value or something in order to support your process cost.
But yeah, that is true. But another type of product would probably be even utilizing the mobile olefins to gasoline would be to produce maybe a longer chain molecules that can be used for lubricants. But that was out of the scope of the study.
Okay. Thank you.
Yeah, welcome.
Thank you. Do you have any more questions? Well, then I have another one. You said that the technical development, or there are commercial or these concepts are commercial in each of their own, but not together.
Yes. Mm-hmm.
So do you know of any plans to go further with this, or is it because of the financial or the economy is not really in place and there are no further technical development, or do you know anything about that?
I know that there are thoughts of trying to implementing it in a smaller scale to see also other technical bottlenecks that can arise from this integration, and also investigate, as Peter said, the different options for producing products of higher value that can be combined together with the production of biofuels. So there are thoughts about that. Whether they are going to implement it in the very near future is something unknown.
And then also I wonder if you see this concept mainly for a Swedish perspective on the Swedish market, or you see is it a more international viable system, or how do you think about that?
Well, we consider small to medium scale plants, having in mind, of course, Sweden. And actually, it's more suited to consider 50 megawatt plants. It's very interesting, actually, because a 50 megawatt plant in Sweden is considered as a medium scale plant, while if you go to other countries in Europe, this is considered as a big scale. So big and medium is something relative. So everything depends on the local availability. So that was also one of the reasons that we limited ourselves to 50 megawatt plant. So from that perspective, yes, it can be considered as an international, so to speak, installation. But we also took into consideration the Swedish standards. Probably the process economics are way better if we increase the size, of course, of the plant. And if we go to capacities around 200 megawatt, probably it will offer better economies of scale. Yeah,
as long as you don't increase the price for the feedstock.
Yes.
And did we have another question from Alsi Nasir? You had raised your hand.
Yes, this is Nasser. It's from Imo University. I have a question. First of all, thank you very much for your interesting presentation. I really enjoyed that. In your calculation that you presented, did you consider the new type of the separation and purification? Because basically between 30 to 70% of the chemical plant is related to the separation and purification. And if I'm not wrong, if you consider the new type of separation, such as membrane separation, there will be a significant reduction in the final cost. Did you consider this one in your calculation, or no, you just use the existing industry?
No, well, yeah, we try to use processes that they are already reliable and in the market with a low risk of implementation. And we also didn't want to include the processes that they are actually involving very high pressures, that typically membranes use higher pressures than PSA units, for example, that they are used also in polymer plants, that they separate the olefins or isomers there. So no, from that perspective, no, membranes were not considered. Mainly the separation was based on the PSA units.
Thank you. And then I think Peter Skagelind had another question, if I understood your...
Yeah, I just checked here because I think this lubricant you mentioned, that I've heard from several places that could be of interest. I think there is some high demand or something like that for lubricants on the market. It's not, I don't know so much about it, but I think that could be some interesting, if you would like to find a more, if that's possible, high value also product during this process. I had one more. This if you take even smaller plants, I think you mentioned also this 5 megawatt or something like that. What is how much did you calculate on that one? What was the investment cost of that type of plant?
You mean the investment cost for a 5 megawatt plant?
Yeah, the investment cost, not the process cost. I mean the investment cost.
Let me see. I have to check the numbers.
Okay, you don't. Okay.
But you can definitely find them in the report. So I found it here. It is 188 million crowns per megawatt of megawatt biomass. So then you have to.
How you calculate like that? 108 per megawatt. Okay. Okay. Thank you.
You're welcome.
So we still have time for more questions, if there are any. No. I think then I don't think I had any more questions at this point. So
but if anyone has, they are very welcome to send me an email and contact me. That's of course.
Yes, your email address are on our website there. So thank you very much then, Efthymios, for your excellent presentation and an interesting discussion to all of you. And go on our website and check for Efthymios' final report. And thank you so much for today.
Thank you.
Bye.